So, very good morning, everybody. Today we are going to start a general discussion on process memory layout. For all those people who are already taking C training with me, they already have basic idea about process memory layout. But that process memory layout that I explained to you earlier is a half story actually. Full story you will get today. I wanted to tell you this right from the beginning, लेकिन कोई जरूरत नहीं थी मतलब आप लोगों को कंफ्यूज करने की, इसलिए मैंने आज तक बताया नहीं. Okay. So today I'm going to tell you things that you've not known, that you've not known in the process context. Okay. We know that when we load our program from secondary storage to RAM. So in the last class we have studied virtual page to page frame mapping. So large scale virtual page to page frame mapping happens when we load our program into memory. Another thing, when we load our program into memory, there may be that our code gets loaded in the code segment. Some initial data gets loaded in the stack segment. Some other data gets loaded into the data segment. If there is some global or constant data, some macros, all these things will get loaded or may not get loaded. But one thing is certain, process have symbol table that was created at compile time. That symbol table is definitely loaded. In that symbol table, there is a list of system calls. There is a list of all C libraries that are going to be used in your code. So that symbol table is certainly loaded, which contains list of all symbols, all kernel routines, all system call routines, all C libraries. There is a list of those. And if any of those system calls are happening immediately, those system call routines are also loaded. What did I say just now? The system call routines are also loaded. Means the system call routines are pulled out of kernel and loaded into the process context so that to execute this code, control does not have to go inside the kernel. Okay. A process is an instance of program in execution. It occupies some space, actually, page frames. The actual memory that is occupied by your program is called page frame. It is seen as a live runtime scheduling entity of the operating system. The operating system always work on only page frames. Operating system always work on only that part of the code that is currently in memory in page frame and is executed. Yes, Jagriti? There it is, shared now. So the operating system stores information about process in kernel data structure context. All the information about the executing process that has to be stored, that has to be saved, is stored or saved in kernel data structure called task struct. In Unix, it is called process control block, and in Linux, it is called uh, task struct. Okay, just a minute. Let me put it to silent. So theoretically, the process control block or the process descriptor or the task structure are all same, but they have different names. Every process has a virtual address space. In a fictional computer with 16 address lines, suppose you'll have 2 to the power 16, that is 64 KB size of the virtual address space. In a 32-bit system, it is 2 to the power 32, that is the size of the process context on a 32-bit machine is 4 GB. Whereas the size of the process context on a 64-bit system is 64 GB of virtual addresses. Remember, of virtual addresses only. Okay, 64 GB of virtual addresses, not the actual memory. So the virtual address space spans from low address of 00, all zeros here, to a maximum of this FF on a 64-bit system, which is 64 GB of virtual address that is created. Let's have a look at this virtual address now. When a new process is created, the operating system divides up the process virtual address space into homogeneous regions called segments. The process context is divided into segments. We have known 4 segments. Okay. The segment is why we have created segment. Suppose you have some chairs. You arrange chairs in a row. Okay. Then you arrange chairs stacked over each other. Okay. Then in third, you arrange chairs in a circle. So you have 3 different arrangements of chairs. Similarly, in memory there are pages. The pages have different arrangements. Okay, all different arrangements of the pages in virtual address space is called segment. Like the stack segment will have a different arrangement of pages. The library segment will have different arrangement of pages. Data segment have different arrangement. Code segment have different ways to arrange the pages. Like in data segment, there is heap. The heap is arranged in a tree. The stack segment have local data where the pages are arranged in a stack. So therefore, because the arrangement of pages is different, therefore different segments are created in the process context. The segments will have attributes. Every segment will have start and the end address. Every segment will have different protections. For example, the library segment and the code segment have read only permission of protection, whereas the stack segment have both read write. Data segment heap have both read write. Uninitialized data have both read write. Initialized data have read only because you store constants there, macros there. And there are different mapping types also. Like in heap, the mapping is like pointer to allocated space. Whereas in libraries, the mapping is like if it is a dynamic library, then the mapping is like a link from the process context to some place where the routine is kept. All pages belong to the segment, share the same attributes. All pages in a particular segment will have same attributes. Another set of pages in another segment will have another attributes. The segment is called mapping. Stack segment, code segment, data segment, library segment. Okay. The segments are also called mappings. Okay. Now this is what you've known till now. The code segment called the text segment. You know that there is something called data segment, which is divided into 3 sections: the heap, the initialized, the uninitialized portion. The library mappings, there are 3 segments. One is shared libraries, another is static libraries. In between, there is also that does not occupy space, though it has only links to dynamic library, DLL, dynamic link libraries. Then the high address is a stack from which grows downwards into the stack segment. Stack always starts from last, and goes down into the process context. Text is code segment. The actual opcode and operands, including the included files, hash include files, generated by object dump hyphen source. You can use object dump hyphen source to see the code in the code segment. For example, if you have some program here, we have this program, we have this stacker program. If you compile it and use object dump source, मैंने आप लोगों को बताया था कैसे यूज करेंगे, कैसे यूज करते हैं इसे. तो वो executable file, source file नहीं. So executable file is this. So we do obj dump hyphen source dot slash file name. ये आ गया. This is code segment, actually the assembly part, assembly coding. नहीं, असेंबली कोड को फिर ट्रांसलेट करके हाई लेवल लैंग्वेज में ले आते हैं, वो भी होता है. मैं आगे दिखाऊंगा हाउ यू कैन हैव लाइन बाय लाइन असेंबली कोड एंड कोरस्पॉन्डिंग हाई लेवल लैंग्वेज सी प्रोग्रामिंग. आई विल शो यू दिस. बहुत ही अच्छे से मैं बताता था ये आप लोगों को. I used to tell this very nicely to you earlier. C programming, I used to tell you so nicely. And prior to C programming, there was assembly programming. I used to tell people very nicely. I learned myself very nicely. And before, people who came before me, who became engineers in 70s, they used to use binary instead of assembly. So it made a transition from binary programming in binary, then programming in assembly, then programming in high level languages, and so many programming languages went on for 50 years now. Since last 50 years, people are programming in high level programming languages like C, C++, Java, blah blah, Python. And now that is changing. Okay, so to change, we will have tools that will generate code for you, but you have to give proper inputs to generate code, and you should be able to analyze code. Means your expertise in high level languages, programming level expertise will not be enough. You have to have very deep understanding about how the code is working. Then only you will be able to analyze and customize it for your requirement. Now, for that we have to learn two things: Rust and LLM together. For good news for people like you who are in COTS, 1st of January next year, I will make a big transition from high level language to generative AI, where we will learn Rust and LLM and make ourselves ready for what is coming in 2030. By 2030, C will be superseded by Rust plus LLM together. Okay, so जब वो आएगा समय, so by before that we should prepare ourselves and be masters for what is already coming in. Okay. Meanwhile, nobody will be able to directly jump to Rust. Okay, you can learn Rust, but nobody will be able to directly jump there using Rust and LLM together. Nobody can do that directly. You have to learn C and master C. Then only you will be able to go there. Okay. Okay. So having said that, so coming back to this, I'm just drawing the picture of what comes ahead for people who are already in course. Okay. So code segment, the assembly portion is here. You can see the C code also. I'll show you. This machine code resides within the process virtual address space in the text segment or the code segment. All the pages occupied by the text segment have read execute permissions. Okay, and मैं दिखाई देता हूँ कि this is what you have in the code segment. There is no point in showing this. So इसका assembly version मैंने दिखाया अभी. This is compiled executable ELF. Okay, all the pages occupied by the text segment will have a read-only permission. Okay, code execute at the lower end of the virtual interface. Lower end से नीचे से ऊपर की तरफ execution हो जाता है. ठीक है? It never starts from 0000 address. हाँ, 00 address is here, and it goes upwards till FF. At the bottom you have 0000, but the text segment never starts from 0000. Text segment starts at some arbitrary address within the process context. This arbitrary address is determined using address space randomization algorithm used in Linux. It is always random, but certainly never 0000. This is a security feature actually. Nobody knows that the code segment starts from there. Then what is 0000? Well, it is null, null macro, which will always point to address 000000 and will have no data type associated with it. That is null. The starting address of the text segment is set up through Linux security mechanism like address-based randomizing just now. Now, this second segment, data segment. In this place, you know very well that it has three parts: a heap, uninitialized, and initialized portion. Okay. You know this already. Now, in order from the low address it consists of initialized segment, and then above it contains heap section. I'll tell you more about heap section. Refers to the memory region reserved for dynamic memory allocation, and this region is arranged in a special kind of tree called a heap, or Fibonacci heap, or binomial heap. There are three types of heaps that are used in process context. Okay, I'll tell you about all the three types of heaps. What is the architecture in advanced data structures? The text initialized and uninitialized segments are fixed in size. All the uninitialized and initialized data will be global in nature and will be decided prior to execution of the program, will be decided at the time of compilation only, and this will never change throughout the lifetime of the program. Whereas the heap is dynamic in size, and heap will have, as and when you allocate memory, it will grow or shrink. Okay. All shared libraries that are used in the library segment. Library segment is further divided into three portions: static libraries, dynamic libraries, and shared libraries. I have told you about all these three. If you have any doubts, you can ask me now. Okay. Then coming to the stack segment. This I'll tell you because you have been using it very frequently. The stack segment, we are taught to write nice modular code divided into functions, and every functions will have local variables. All the local variables are stored in stack. Inside the stack, I have told you the concept of stack and the stack frame. If you don't know, ask me now. The concept of stack and the stack frame is used in the stack segment to store the variables, local variables in different functions. Okay. So stack can grow. Yes, Utkarsh? स्टैक के फ्रेम में जो आर्ग्यूमेंट्स पास होके आए हैं वो होते हैं. इसके अलावा local variables, all the local variables that you declared in the functions, that are also stored in the stack frame. Both local variables and the formal arguments that are passed in argument, both are local in scope. Yes, Raman? Every stack frame of a function have different size. The moment the function is called, invoked, and loaded, it will know what are the arguments are coming, what is the size of formal arguments. It will also know right at the beginning that what are the local variables being created, and stack frame will be created right in the beginning. That's why I always tell you to have your stack frame, all the variables declared right in the beginning of the function, because the declaration section of the function is different, isn't it? Because the stack frame has to be created, and the size of the stack frame has to be determined before the function is loaded. If in case you declare your variables not in the beginning of the function but somewhere inside, just like कई लोगों को मैंने देखा, they do for loop, and inside for loop they declare int variable, and they say that okay, the scope of the integer variable declared inside the for loop will be restricted to for. That's fine, but at the same time, stack frame creation will take more time. So function invocation and loading will take more time. Okay. Yes, Raman. Well, stack has to grow. Okay. If the stack grows from some place inside the process context and grows upward, that there is one time will come that the stack will go beyond the process context. So for that, to prevent that happening, you have to have some kind of a check mechanism every time you are using the stack. Is it going beyond the bounds? No. On the other hand, if it grows downwards, then you don't have to perform that check. But that grows upward, the same concept applies to that also. You have huge amount of space available inside the process context. You can't go down because down you have data segment, initialized and uninitialized data that will all get overwritten. Yes, Utkarsh? Stack is a segment, is a region in which the pages are arranged in a certain manner. Stack segment is a region. Inside the segment, the pages are arranged in a particular pattern. Now, within that stack segment, you create a stack. Within that stack segment, you will create a stack. Okay, and then within that stack, you will create stack frames as and when the functions are loaded. For every time a new function is loaded, a new stack frame will be created. I think everybody knows this concept. Suppose this is a process context. Inside the process context, suppose this is your stack segment. The stack segment. Inside the stack segment, the moment the main function starts, a stack is created. The stack. Now the stack, the moment you call the main function's entry will be created in here. Yeah. And a corresponding stack frame for the main function will also be created. Okay. Suppose the main function calls another function. Then a new entry will be made for another function. And a new stack frame will be created for another function. Okay. Suppose you create a child process. Then for the child process, a new stack will be created when copy on write will happen. The new stack for child process, which will have its own stack frames. This is how stack is arranged. Okay, so memory is allocated in the stack region to hold metadata that has the function call, function's local data, function's formal parameters. Parameters passing and the function return mechanism also work. Even the return values are stored. This metadata region of this function is called the stack frame, where all the function's local data is stored. The stack frame holds the metadata necessary to implement the function. Call parameters, use return value mechanism. The exact layout of the stack frame is highly CPU dependent. I have explained you here that the stack frame is a simple linear array kind of stuff. But no, stack frame has its own architecture, which I'll tell you in advanced data structures. It's one of the key areas addressed by the CPU ABI application binary interfaces. How the stack frame will be created will MMU will be having some role to play in it. On an IA32 processor, the stack frame layout essentially is follows: high address of the stack frame, that is a starting address. Function parameters. What are the parameters that are passed will be stored. Then return address will be stored. If the function finishes, it is going to return something from the called function to the calling function. But in the calling function, when the return value will come to the calling function, where will the return value stored in some variable or some pointer? That has to come as argument into the stack frame. Then it will also have some saved frame pointers, if any. Local variables will come after that. Then after that, the stack pointer lower address where the stack frame will finish. So this is the architecture of stack frame. Okay, I'll give this to you. This is important. Data structure important because we will be using it in advanced data structures. We'll be programming about it. So this is the architecture of stack frame. It is not, I told you, it is not linear like array. I manage as a diagram. It's not like that. It actually looks like this. The high address and the low address, in between you have four things. Function parameters, all the arguments being passed, the return value, where it will return, then the frame pointers, which I'll explain later, the local variables that are being declared in that function. Okay, now consider pseudocode. I have a main function from where you're calling the foo. So you have a stack frame created for main, you have a stack frame created for foo. When the foo function executes, it calls another function bar. So third stack frame created for bar, and when the bar function executes, it calls jail. For 1, 2, 3, 4 stack frames are created. One for main, for foo, for bar, for jail. Every function invocation is represented as a runtime by the stack frame in the process stack. You will have 4 different stack frames. Every time the function is called, arguments are passed. Every stack frame will have high address, low address, return value, high address, low address. Then 4 things: parameters, return value, frames, and finally local variables. Okay, always. The very first function when you start your C program is by default 2 stack frames will be created. One is libc and underscore libc underscore start underscore main. This is a library provided by the Linux systems which will find the main function in your program. And first this library will get loaded into the process context and load the main function. This library. It will have its own stack frame which will contain information about the program like symbol table. Then the main function will load. Main function will have high address, low address plus 4 things. 1. Command line arguments, return value, local variables, and some additional frames. Okay? So this will have symbol table. Then main functions, foo, for bar, frame, everybody will have their own stack frame in the data structure that I explained you just now. And the stack will keep on growing downwards automatically via gstack. You can look into the stack when you use gstack utility. Today I'm introducing you to these utilities. Tomorrow we'll be using it manually with the GDB debugger. I have to tell you about backtrace, about attach in GDB. And this is the third thing that we use gstack utility with GDB, using which we can look into the stack, what is the identity, what is the contents of stack. The address space is shared between user and kernel space. Astonishing fact. Till today, you have learned that the process context is in user space, not kernel space. You have learned this? Let me change the perspective and keep it right for you. The address space is in user space, fine. Virtual address space is in user space, but some portion of it is shared in the kernel space. So it is actually like this, the true complete picture. Suppose this is your kernel space here. Okay, kernel space where you keep some memory, some region of memory here, and some other region here. This is your user space. Okay, so let's draw the line, the separator between the user space and the kernel space. So above you have the kernel space and below have the user space. And when the process context is created, the process context is created like this. Some portion of the process context will be in the kernel space. All the processes, always. Here you'll have stack segment in which you have data. local data, the stacks and the stack frames, everything. What do we have here? This address at which you start the stack frame, this address is the high address. Yes. But there is something about this. The address space is shared between user space and kernel space. Every system call made from the executing program is a legal kernel hack that will take the control inside the kernel. This is achieved by having dynamic or shared libraries memory mapped into the virtual address space. Now, every system call that will execute will be coming from either system call made from some code segment or some library being executed from library segment or dynamically executable library segment or dynamically linked or shared libraries from wherever. So there are four ways of hacking, legally hacking the kernel and executing the kernel code, executing the system call routines. The system call code is actually within the kernel address space. So it will be so cumbersome and tiring to jump to the system call from the executing process. And it will be costly with respect to resources and time. The system revectors the CPU instruction pointer to the address of the system call. Now, how it is difficult to change the context, move from process context program counter to some other counter to execute some code inside that kernel, which is of course within the kernel address space. So another astonishing fact. Recall the fundamental rule of virtual memory. You cannot look outside the box. Rule of virtual memory. You cannot access anything. You cannot execute anything outside the process context. This is the fundamental rule. No? So, in order for this whole scheme to work, rule number one, you can't go outside the virtual address space. The kernel code is not only outside the virtual address space, but is it inside the kernel. In order for the whole scheme to succeed, even kernel virtual address space. Yes, please note, the kernel address space is considered virtual by the process, must somehow be mapped into the virtual address space. So some region of the kernel space is mapped into the virtual address space. Some region of the kernel is mapped into the virtual address space. Okay. The stack segment does not sit at the top of the address. No. यही सीखा था आज तक. That at the top of the process context you have the stack. That is one level of learning. Actually, there is one more segment above the stack, and that goes encroaches into the kernel space. The operating system creates the process virtual address space, arranges for the segments within it, stack segment, library segment, code segment, everything fine. It also reserves some amount of virtual memory. At the top end for the kernel or operating system mappings. Every time you map some operating system code, that operating system code has to run, isn't it? This region is used for that purpose. It also reserves some amount of virtual memory at the top for the kernel, also in the kernel code, data structures, stacks, and drivers. ये होगा यहाँ पे. These things from inside the kernel will be used and stored in this segment. Okay. Astonishing fact number 3. This segment, which contains kernel code, kernel data, and kernel data structures, is usually referred as kernel segment. A new segment introduced today, kernel segment within the process context. Okay, right? The amount of memory kept for kernel segment is tunable at kernel configuration or installation time, called VM split. And this region, which splits this split, is called VM split. That splits the process context away and the kernel segment. Virtual memory split into user space and kernel space. VM split. Okay, this is the point in virtual address space where we split the address space between the OS kernel, the user memory, text, and the rest of the process context. Ooh, okay. We have this here. Okay, so this is how it looks like now. The process context. This is a complete picture of the process context. This is how it looks like. Okay. VM split. If you are executing 1, 2, 3, 4 processes, then every process will have kernel segment, kernel segment, kernel segment, kernel segment. Suppose. Yes, Raman? I will answer this question to you later. Okay. Let me complete this process layout architecture complete. Then we'll see how the processor operating system uses the process context to execute their intelligence. It is going to be discussed anyway. Okay. Now suppose you have a kernel space and you are executing 10 processes, 100 processes. All the 100 processes. Meherban Ali, first of all, welcome. Meherban Ali, you are I remember you're a handsome guy, ex-evolution. The answer to this question is yes. Meherban Ali is asking that underscore underscore libc underscore start underscore main also have a return address, and the answer is yes. It returns 0 for success. It returns -1 for failure, a kind of failure from where you cannot recover, but it also returns +1. When this library returns +1, it means that you can write a recovery routines for it. Okay. Okay, coming back to this topic. Now, the process context have kernel space. Suppose you are executing 100 processes. So does that mean that all the 100 processes will have 100 kernel segments? The answer is no. You will have one common kernel segment. Every process context will do encroachment into that one common kernel segment. Okay. In that one common kernel segment, we will load all the system call routines, libraries, kernel threads, uh, kernel libraries, whatever are required. And all the processes will fetch, you know, the kernel code from here. One common kernel segments. Now, every process context will have symbol table, which will be maintained by underscore libc start main. That symbol table will contain mapping that whenever you will make a system call routine from the text code segment or library segment, the the mapping will go into the kernel segment. The corresponding kernel code will be loaded into kernel segment, and that mapping will map there and execute it from there. So the kernel segment will be one common kernel segment in which there will be system call routines from used for every program executing in the program, and every program will have its own symbol table being maintained by libc start main, which will do mapping from their own respective process context into kernel segment, into their respective routines. All the routines, listen this carefully, all the routines that are loaded into kernel segment are loaded as kernel threads. All the routines that will be loaded into kernel segment will have reentrant property. A reentrant property means you can execute multiple instances of the same kernel routine from the kernel segment at the same time. Suppose four processes all give a call to system call, clone, clone system call, which I'm going to tell you soon. Then you will have clone system call routine executing simultaneously for all the four different processes. Four instances of clone will be created and parallelly simultaneously. This property that a particular system call routine could execute multiple instances at the same time is called a reentrant property of a system call. Such kind of code will be in the kernel segment. Okay. All right. Any questions? Okay. Now let's go ahead. There is a system call called process control, PRCTL, which we'll be using in our program, where we'll check or set the process parameters. PR underscore set underscore mm is used to set the process parameters in this process context. Okay, we will be using that when we'll start programming. So next class, we'll be using PR system call, PRCTL system call, mmap system call, mprotect system call, and some commands that will tell you with GDB how to look into the stack segment. Okay, that is the topic for us to do in the next session. For today's session, if you have any query, you please ask me now. Yes, Shivam. Mhm. So Shivam, your question is that the initialize section has read permission. How could you modify data there? Well, at the compile time, suppose you have created some constants and given value to those constants, like size is equal to something. All such things will come here, which are not supposed to be modified during the execution of the program. All the things that are supposed to be modified during the execution of the program will come in an initialized segment, even if it is initialized. So primarily, macros and constants will come into initialized section. The rest variables will come here in the uninitialized section. Yes, anybody else have any question? Chalo, very nice. So, yeah, there is something. Somebody, Shrikant, yes, tell me, Shrikant. Mhm. Well, dynamic libraries. For dynamic libraries, you will have listen carefully. For dynamic libraries, you will have links provided inside the process context. Links provided inside the process context. First of all, let me tell you, Shrikant's question is, what is the difference between dynamic libraries and shared libraries? This is his question. And the answer to this question is that dynamic libraries will have links provided inside the process context, but the actual library is kept somewhere else. Today, you understand that the actual library is kept in the kernel side. So, whenever you want to use those libraries, the link will be used from the library mappings into the kernel segment where the library is kept, and that library will be pulled into libraries mappings and will be used executed. Whereas, now suppose, whereas for shared libraries, the library will be kept in the kernel segment. Link will be provided from library mapping, fine. But whenever you want to use it, it will not be pulled into the rest of the process context for execution. It will be executing from there only. So the code will not be pulled into the process context. It will execute from kernel segment in the shared libraries. So if 10 processes are calling the same code, they will execute different instances of the code in the kernel segment only. It will not be pulled in the user space portion of the process context. Okay, right? Any more questions? So there's a question from Meherban Ali on YouTube. If kernel segment is shared among different processes, what if the process changes some kind kernel data structure? Does the change that reflect in the other process also? How do we secure it? Well, every time there is some change happening in the kernel data structure from a process, a new instance of that kernel data structure will be created for that process. Like for example, you created a struct X. Every time you create a structure variable, a new instance of X is created. Structure is created. Similarly, every time the kernel data structure is modified by the process, a new instance of the process context of the kernel data structure will be created for that process. Okay, and that will not intermix with other process contexts. So, any more queries you have about today's discussion? You can ask me now. Okay, I'm going to end this session now. You can ask the queries later also in the discussion forum. Okay, thank you all. Thank you very much.